Hi there. Yeah, I'm Pete, and I'm going to be talking to you about learning 3D style, particularly in the context of computer-aided design or in CAD modeling. So yeah, this is work I've done as part of my PhD, and in collaboration with some people at Autodesk. These are my collaborators on this, and this work was just recently accepted to be published at ICCV later this year. So you can get hold of a preprint at this link or using that QR code, and the code and data that you see in here will all be publicly available within the next couple of weeks. So I'm going to jump right in and explain a bit about, well, what's a BREP, that word that's in the title there. So in computer-aided design, this is the standard representation for 3D solids. It's very different to some other representations that we normally see in deep learning or machine learning. They're precise analytic representations of solids, so they contain information about the precise boundaries of each face and information about how these are connected together. So for this loop here, it would have information about the radius of that circle and the center rather than specific points that are sampled from it. So like traditionally in machine learning, we see 3D research focusing on point clouds, meshes, a little bit on voxels, and even perhaps projected views. But each of these representations is lossy or is sampled from the underlying data. So we even need very big amounts of information to describe all of the detail that's there in the solid, or we kind of lose information and we lose detail. So these are not really ideal for working with style, and they're not used in the computer-aided design processes. So we want to be able to work directly with those boundary representations. So how do we encode a BREP and use this in a deep neural network? So we've used an encoder called UVNet, which starts off by applying a grid over each face and doing traditional 2D CNN convolutions on this. So we take a small 3x3 grid that we move across each face to summarize the features within that grid. Then by using multiple layers of this, we gradually summarize higher and higher areas of that face to learn higher level patterns that are shared throughout the different solids and higher level features. After representing each face in this way, then we aggregate the information for the face to a single vector or a single number that describes that face and the shape of it. And then we use the information of the BREP to propagate this information between adjacent faces using a message passing network or graph neural network. So then we start to look at beyond the features of an individual face. We look at how are these faces connected to each other and learn higher order features here in terms of the topology of the solid. Once we've finished with the graph neural network, we then aggregate that information into a single representation for that solid. So this single number here will tell us about the content of that object. Is it a cat? Is it a house? Is it a car? And similar objects will have similar numbers there. But what we're interested in here is learning to represent style and measure style rather than the content of what's in the solid. So to do this, we draw on techniques that were first used by Gattis et al. In about 2016, where they showed that if we extract statistics at each layer of the CNN, then these statistics summarize things like the correlations between the features, and we can use this to understand the style at that layer of abstraction, moving from like fine low-level details up to higher order details. So here we're going to generalize that technique to 3D so we can apply it to these CAD models. To understand a bit about this statistics, at every layer of each of the networks, we have a matrix where every row corresponds to one feature that's detected at that layer. So this could be rounded corners or a flat surface or a beveled edge and things like this. By taking that feature matrix and multiplying it by itself, we get what's called the gram matrix, which describes the correlation between all these different features. And this is a really good indicator for style at that layer in the network. So by using one of these gram matrices for every layer in the network, we can then compare these between two different solids and measure how similar or how different is the style at these different layers. Okay, so to think like, can we verify that this actually works in 3D? It's been shown in 2D, but the features we have here are quite different. Rather than colors and pixel intensities, we're looking at X, Y, and Z positions. We're looking at normal vectors, saying which direction the faces are pointing in and things like this. So to test it, we used a synthetic data set where we took fonts, 2D fonts, because they have a good style label that comes with them, and we extruded them into 3D. And then we looked at the network and used a method called linear probing, where we say at each layer, how good is that gram matrix if we want to predict which font this letter is. And we found that for the UVNet encoder shown in blue, it was very effective in the lower layers of the network. The orange here represents the current state of the art for this technique, and the green and red show the method we've tried applied to some other representations like point cloud and mesh. So yeah, working with the B-rep here seems advantageous. So how can we then actually use this style signals for something useful? So we first look at, can we find solids that share similar styles based on this? So using this data set, you can see here, we've got on the left is our query. So this is our input solid, and we look in our database of other extruded fonts and say, can we find other letters that share the style? At the moment, we're looking at the kind of highest part of the network. So we see that high up in the network, it's really looking at the content. So we're finding different letter L's, and it's got the same content, but the style is different. We have a different font. But then according to our hypothesis and assumptions, if we swap this to the gram matrix of the lower layers in the network, then we should be able to match different content that shares the same style. And we see here the nearest results. We match this same wiggly font, but the content is very different. This is no longer anything like the overall shape of that L. To see how this compares against the existing methods, the PSNet here was the state of the art, and these were our method applied to point clouds and mesh. We see UVNet encoder, as we proposed, to be best suited to this task, matches the query for all of the 5 nearest neighbors for each of these 4 fonts, whereas the other methods make some mistakes or have letters of a different font being matched. Okay, so we've shown using like the style distance to find similar solids, but we wanted to then say, well, can we get anything more useful out of this model? Can we get any good feedback to a designer as they're designing a solid about how to match its style to some kind of target? So for this, we've done something called gradient visualization, or back propagating the gradients of our loss back to the input solid. So in this case, we have 2 letters of the same letter class. They're both a C, but they're of a slightly different font. And the black lines here indicate the gradients from our model. So here they're showing which direction the model would like to move that point in to better match the style between these 2 solids. The lines are largest around this areas at the end of the C, which when we look at, we can see are the parts that vary most in style. If we change the style to be quite different, so we have this kind of squarity at the bottom, we can see that on the top, with the model is trying to slightly square out these corners, or square out these curves to better match the style. And on the lower one, we can see that the flat surfaces that don't appear in the solid above is trying to curve these out downwards to match the styles. But in each of these cases, we're looking at the same letter, but the same letter with different styles. So then we say, well, what about if we have different letters and different styles? Can the model still just try and match the style, or is it also going to try and match the content? So if we look in this case, we can see again, we have a similar gradients, which are suggesting that we should try and move the curve out to be more kind of square to match the bottom. We notice it's not trying to move this part of the solid in, so we can see that it's not trying to match the content in this case. It's trying to make the styles more similar. So in the examples we saw there, we have, so just jump back to this. We have these different layers that we combine to form the style representation. But then we have the question of, well, how do we know which layers are best to use? For the case of fonts, it might be the first and second layer, or even the first four. But for different types of objects, it could be different layers. And even between different end users looking at the same objects, since style is so subjective, they may have their own interpretation of what that means and which layers they prefer to use. So what we did is we said, can we optimize and find the best layers based on just a couple of examples that the user provides? So this is known as like few shot learning. And what we did, we took, for each of the fonts shown here, we took a few examples as an indicator of the target style. And as negative examples, we took a random set of letters from the remaining data set. And we said, if we measure that style metric, how good it is, do we get any improvement by providing these positive examples and updating the weights? And for the 6 fonts we tested, we saw an average by just providing 2 user-selected examples, we can tailor the style distance metric to those examples, getting an improvement of about 12 or 13%. And this increases as the user provides more positive examples. So if they're providing 10 examples, we saw up to average of 27% improvement in that style metric. And this is using just random negative examples. Okay, so far we looked at this synthetic data set of fonts, but how does this work on real world data? Especially given that in the real world, for BREPs in particular, there aren't any data sets out there that have labels for style, and there aren't even many that have labels for content to pre-train our encoder. So in this case, we used a data set of CAD models that we pre-trained using point cloud reconstruction. So it's completely unsupervised pre-training. And this was novel work to be able to do 3D style learning for CAD models with completely unsupervised methods. So on the very left, we have our query objects that we want to find similar style objects to. And then here we have our work. And then this is the previous state of the art that we adapted to be able to work in the unsupervised way as well. So we can see that if we look at row E, we have this kind of Lego block as our query. UV StyleNet matches, the nearest 5 matches are all different shaped Lego blocks. They share this notch style, but we have blocks of different shape and sizes, even different number of notches. If we look at the previous state of the art, then we see that similar sized blocks are matched, but the style is actually quite different. Okay, and then applying the few shot learning to this as well, and kind of summarizing the process that's involved here. Here's an example where the user supplies this solid with these rounded edges as their query. they get back some query results using just a guess at the weights. We just use uniform weights in this case. Then they select from here, okay, actually I'm interested in this rounded style, this filleted style. So they select a positive example with the filleted style and a negative example that has these flat edges. Then optimizing this updates the metric to focus on this part. And now the new query results, the closest examples also match that filleted style with other flat edged solids being pushed further away. To quantify the results on this real world data, we manually labeled a small subset of this data set into the following categories, and then did a similar experiment to before, where we measure how good are these gram matrices as a feature for predicting the classes between these different style classes. And in each of the cases we tried, we saw an improvement over the previous state of the art. Okay, so to kind of summarize and wrap up what I've shown here, like you can read a lot more about this in the paper, but the key takeaways are that we have generalized 2D style principles and assumptions to 3D shapes. So there's been some work on this for point cloud, but we've shown it also for mesh, and in particular for boundary representations. And we've shown really the advantages to using these boundary representations over the alternatives. We've demonstrated that we can generate useful feedback for a designer that can be used during the modeling process. And we've shown that our method is effective without any labels. So we don't need any labels for style or for content in order to train and take advantage of our model. And then finally, we've demonstrated better results than the existing state of the art on a range of tasks. So now I can open up for questions. If you have any questions that I can't cover here, like feel free to drop me an email. Or if you want to get hold of the code, just drop me an email and I can let you know as soon as it's available, and it should be in the next couple of weeks. Okay, thank you.